Bismillahirrahmanirrahim. Today we're going to talk about chapter 9, which is about principles for controlling harmonics. Harmonic problems are due to the nonlinear load that inject excessive harmonic current, and also interaction between harmonic current and the system frequency, because we said that it's going to create resonance. When a problem occurs, the basic option for controlling harmonic are to reduce the harmonic current produced by the load, and we're going to talk about several methods that can be utilized to reduce the harmonic current produced by the load. Adding filter, and we have already discussed this one. Number 3, modify the frequency response by using inductor, capacitor, or even filters. Let us first of all look at the first point, how to reduce the harmonic current produced by the load. We can reduce the harmonic current produced by the load by either adding line reactor or transformer in series, since that will significantly reduce the harmonic, as well as provide transient protection benefits. Okay, so we can reduce the harmonic by adding a reactor or by adding transformer, because actually the transformer, that is a very large reactor. Number 2, by using transformer connection, since transformer connection can be employed to reduce the harmonic current. And this is just an example. We have over here the primary connected as delta for the transformer, and then this transformer will have two secondary. One of them is delta, and the second secondary is Y. So as a result, by doing such kind of connection of the transformer, we're gonna produce over here what we call it 12 pulse. If we use only one secondary, we're gonna have 6 pulse. But since we are utilizing two secondary, one of them delta, the second one is Y, there will be a phase shift. So as a result, we're going to have 12 pulse or 12 diodes connected. And that, what will be the effect of doing this one? It will reduce the 5th and the 7th harmonics. We discussed this one already before. Then if we have delta connection transformer that can block the flow of the zero sequence, right? So those will keep circulating and then it will not go to the load. We can also utilize what we call it zigzag or grounding transformer, also to shunt or to take out the treble harmonic as well. Okay, so we can take out the treble harmonic by using delta or by using zigzag or grounding transformer. When we talk about zigzag, this is a zigzag transformer, and we're going to talk about it later on. But over here, also we are talking about what we call it grounding transformer. What is a grounding transformer? Grounding transformer is used in a 3-phase system to provide a ground path to either an ungrounded Y or delta connected system. So if you have, for example, over here a normal transformer, we call power transformer, with Y delta. Of course, over here, since we have delta winding on the secondary, then nothing can be connected to the ground, right? In delta, nothing will be connected to the ground. Then how to connect the system to the ground? By using either, we call it zigzag transformer, and this is how zigzag look like. Okay, I will talk about it inshallah later on. And now the system can be grounded, or by using what we call it Y delta unit. And of course over here this delta will not be connected to anything. But look at the Y will be connected also to the ground. Okay, so this one also we call it a grounding transformer. But what are the difference between the two? The difference between the two is in terms of cost and in terms of size. So we are saying that zigzag connection is preferred as it is more cost effective and physically smaller than Y delta unit. So normally to have a grounding transformer, normally they are using zigzag. Land reactor, or we call it chokes. It is a simple method to control harmonic distortion generated by adjustable speed drive. So over here we have speed drive. This is speed drive. Then of course those will create harmonic, as you can see from the output waveform. Then to reduce the harmonic that is produced by the adjustable speed drive, they are connecting over here what we call it choke or line reactor. The reactor or the choke will slow the rate at which the capacitor on the DC side can be charged and forces the drive to draw current over a longer period of time. As a result, the net effect is a lower magnitude current with much less harmonic content. So this one will be the result. The choke size is computed on the drive kilovolt ampere base. Okay, and over here we are having a figure that shows the relationship between the current distortion with respect to the size of the choke. So over here is clear to say that if we have a total harmonic distortion for the current which is about 80%, then if we utilize, let us say, 3% size choke, that can reduce the harmonic distortion to around 40%. Okay, this is also another sketch that shows the relationship between the total harmonic distortion with respect to the size of the drive with respect to the size of the transformer. Okay. And then over here we have two figures. The first one, this is without choke. The second figure with the choke. Therefore, if the adjustable speed drive kilovolt ampere normalized to the transformer size in kilovolt ampere, if it has a size of 5%, and then we use a choke with 3%, then that will reduce the total harmonic distortion to around 40%, from around 125 to around 30%. Therefore, adding choke will lower the magnitude of the current. Okay, so as you can see that this is without choke, that is with the choke. So we are lowering the magnitude of the current. At the same time, we're going to have less harmonic content. Okay, so as we can see that this one without this, the harmonic content 125%, but with the presence of the choke, we are able to reduce it to around 30, maybe 35 or 40%. It is also important to note that there are other advantages of the choke in the adjustable speed drive application. The effect of slowing the DC capacitor charging rate also make the choke very effective in blocking some high frequency transients. This will help to avoid nuisance drive tripping during capacitor energization operation on the utility system. Isolation transformer can provide the same benefit as a choke, but may be more costly. However, isolation transformer with multiple drive offer the advantage of creating 12 pulse operation, as we have already discussed, right? We have one primary with two secondary, one primary with two secondary. Okay. So over here, if we like to see the current from the first secondary, and then also the current that comes from the second secondary, this is delta, this is y. This is how the current look like. Then if we like to see the current that is coming from the source, this is how the current will look like. So this is the source current. As you can see that it looks like very nice sinusoidal waveform with very low order harmonic. This is another diagram that show the 12 pulse configuration also. So over here we have adjustable speed drive. The first one is fed from delta, the second one is fed from delta Y transformer. So they take the same current from this transformer, but now if you look at the current taken by the two transformer, there is a difference between the waveform of the current that are taken by the two transformer. Then now if you look at the current that is taken from the source, the main current, of course it has lower harmonic content. Okay. When the two waveforms are added together on the primary, the resulting waveform injected onto the utility system has much lower distortion, primarily because the fifth and the seventh harmonic are cancelled out. So over here, again, we are discussing the previous schematic diagram. These two harmonic are responsible for the most distortion for the 6 pulse drive. Okay, so this is the zigzag transformer. This is how it looks like. Okay, so zigzag transformer contains 6 coils on 3 cores. So we have 3 cores, we have 6 coils. Each phase coupled with each other phase. Okay, so phase A will be coupled to phase C, phase D will be coupled to phase A, phase C will be coupled to phase B, and so on. So as a result, the voltage induced will be cancelled. Due to its composition, zigzag transformer is more effective for grounding purposes because it has less internal winding impedance going to the ground than when using the Y delta type transformer. The winding trap, so to the function of this winding, it will trap the harmonic current and prevent them from traveling back to the source, to the upstream. And it protects the power system by reducing the stress of the voltage under a fault condition. So this is over here we have zigzag transformer with the phase shift between the two of them. So the first one is feeding the first load, the second one is the second load. So of course this zigzag transformer can be utilized as a grounding, or it can be utilized also to provide the power to some load. So the advantage will be they will cancel the harmonic. So over there, when they are used as a grounding transformer, they will trap the zero sequence. If they are used to provide the power to the load, they will cancel the harmonic in general. Okay, and of course over here we have again two secondary, and the phase shift between them is 30, t minus 15, that will be 30 degree. Okay, so this one over here we have zigzag transformer that is used for grounding. Okay, so then it will trap the third harmonic, the zero sequence harmonic. It will not allow it to go back to the source. Okay, so it will prevent those harmonic from going back to the source. It will trap them in this loop only. Zigzag transformer can be used as a grounding transformer, which is located close to the collection of a single phase load that produces third harmonic current. The third harmonic current are prevented from traveling back to the source. Okay. Zigzag transformers are often applied in commercial facilities to control zero sequence harmonic components. Zigzag transformers act like a filter to zero sequence current by offering low impedance back to the neutral. This reduces the amount of current that flow in the neutral back toward the supply by providing a shorter path for the current. So as we said previously, that it will not allow the current to go through the source. Okay. The neutral current will not be allowed to go back to the source. To be effective, the transformer must be located near the load on the circuit drive that is being protected. The two most important problems in the commercial facility are the overloaded neutral conductor and transformer heating. Okay, of course the transformer will heat it up also, and when we say transformer, I mean the normal transformer that is used to provide the energy to the load. But those two problems can be solved by using zigzag transformer if it is placed in a proper place, and also we have selected the proper size. Some new commercial buildings include zigzag transformer on the 480 208 volt supply transformer secondary to prevent transformer from overheating. Zigzag transformer located at the supply transformer secondary does not provide any benefit for neutral current supplying the load. Typical result with zigzag transformer show that it can shunt around 50% of the third harmonic. 50%. The zigzag transformer can almost always reduce the neutral current due to zero sequence to acceptable level. The largest zero sequence harmonic will nearly always be the third harmonic in the office building with many computer and related equipment, because over here if we have a building, let us say that contain many computers, of course we're going to have zero sequence current or third harmonic, so that could of course overload the neutral. So as a result we can use a zigzag transformer to be connected on the secondary side. So and it has to be near the load, and that will take care of this problem. Filtering. Okay, so this is the second method that can be utilized to reduce the harmonic by using filter, and we have already discussed this one in previous chapters. So we talked about the shunt filter, we talked about the series filter. Also we talked about the active filter, right? And those how they look like. So we have shunt passive filter, we have series filter, we have active filter. Number 3, modifying the system frequency response. There are a number of methods to modify adverse system response to harmonic by adding or removing capacitor bank, changing the size of the capacitor bank, adding shunt filter, adding reactor to detune the system away from the harmful resonance. Add a shunt filter. This is not only shunt troublesome harmonic current of the system, but it completely changes the system response. Adding reactor. Harmful resonance generally occur between the system inductance and shunt power factor correction capacitor. The reactor must be added between the capacitor and the supply system source. Add reactor in series with the capacitor to move the system resonance without actually tuning the capacitor to create a filter. So over here we have series resonance, over here we of course with that, and with the source we're going to have parallel resonance. Number 3, change the capacitor size, because we know that the resonance or the harmonic order will be given as the square root of the size of the short circuit divided by the capacitor size. So by changing the capacitor size, that means we will be able to move the frequency response. Move a capacitor to a point on the system with a different short circuit impedance. So this is changing the location of the capacitor. Remove the capacitor and accept the higher losses, lower voltage and power factor. If technically visible, this is occasionally the best economical choice. Where to control harmonic? The strategy for mitigating harmonic distortion problem differ somewhat by location. The following technique are ways for controlling harmonic distortion on both utility distribution feeder and user power system. Now let us look at the utility distribution feeder. For the utility distribution feeder, normally the value of R is high, therefore the X over R ratio will be low. Therefore, magnification of harmonic by resonance will be minor in comparison to what might be found inside industrial facility. Utility distribution engineers are accustomed to placing feeder bank where they are needed without concern about harmonic. However, voltage distortion from resonance of feeder bank may exceed the limit in a few cases and require mitigation. When a problem do occur, the usual strategy is to first attempt by moving the offending bank or changing the capacitor size. Some harmonic problems associated with feeder capacitor bank are due to increasing the tripling harmonic in the neutral circuit of the feeder. To change the flow of zero sequence harmonic current, change are made to the neutral connection of Y-connected bank. Therefore, if we like to block the flow of the harmonic or of the zero sequence harmonic, then ungrounded the neutral, leave the neutral to be floated. In other cases, it is more advantageous to aid the flow by putting a reactor in the neutral to convert the bank into tuned resonance shunt for zero sequence harmonic. Harmonic problem on distribution feeder often exists only at light load, so during light load. The voltage rises, causing the distribution transformer to produce more harmonic current, and there is less load to damp out resonance. Switching the capacitor off at this time will solve the problem. So take the capacitor out during light load. Should harmonic current from widely dispersed sources require filtering on distribution feeder, the general idea is to distribute a few filters toward the end of the feeder. So if you have dispersed sources, then the idea is to distribute few filters. Harmonic problems are more common at the end user facility on the utility supply system. So now we are looking at the end user facility. Okay, so solution on the end user. Most non-linear load are located within end user facility, like big industry, and the highest voltage distortion level occur close to harmonic source. The most significant problem occur when there are non-linear load and power factor correction capacitor that result in resonance. When harmonic problem arise in an end user facility, the first step is to determine if the main cause is resonance with power factor capacitor. When it is, the first attempt a simple solution by using different capacitor size. With automatic power factor controller that will keep power factor changing, it may be possible to select a control scheme that avoid the configuration that causes a problem. In other cases, there will be so many capacitors switched at random with load that it will be impossible to avoid resonance condition. In this case, you have to put filter. Installation of filter on end user low voltage system is generally more practical and economical than on utility distribution system. The criteria for filter installation are more easily met, and filtering equipment is more readily available on the market. When the magnitude of harmonic current injected by the load is excessive, industrial users should also investigate means of reducing harmonic by using different transformer connection and line chokes. In office building, zigzag transformer and tripling harmonic filter can reduce the impact of tripling harmonic current on the neutral circuit.